For quite a while, people have envisioned what life might be like in other universes. Because of the James Webb Space Telescope, the most impressive telescope in existence, that question can at last be answered. While noticing the nearest star system to us, Proxima Centauri, which is just 4 light-years away, researchers have seen several curious irregularities from one of the planets in the system, Proxima B. These inconsistencies, called counterfeit lights, have confused the best minds in established researchers. But what are they? Do these lights suggest the presence of savvy life on the planet? Join us as we investigate James Webb's unnerving revelation of city lights that changes everything. The main life that we are currently aware of is on Earth. Since the beginning of human advancement, people have questioned whether there is life elsewhere in the universe. To further such an interstellar pursuit, American space astronomers Jill Tarter and Thomas Pearson sent off the search for extraterrestrial intelligence, SETI, project in 1984. The venture's goal is to gather spaceborne radio transmissions. Radio waves can travel farther and are thusly more likely to be detected by the 42 radio telescopes that make up the remarkable Allen Telescope Array in the Californian outpouring mountains, because they are less scattered or ingested than other types of radiation. But before 30 years, no obvious alien sign has been found. After that, the James Webb Space Telescope's successful send-off helped with the journey to inspect a range of far-off unseen planets circling faraway stars. The largest telescope in the world, which is floating around 1 million miles from Earth and equipped with extremely sensitive finders, will be used. Quite a long time ago, there were no known planets outside those in our planetary system. However, since then, in excess of 4,000 planets have been found orbiting different stars. According to NASA, the universe might contain trillions of exoplanets. The earliest signs of something going on under the surface, past our planetary system, might be seen as extraterrestrial vegetation. The Galileo rocket turned its hardware back toward Earth when it was on the way to Jupiter and tracked down a distinct sign of the presence of plants. The instrument identified the vegetation red edge, VRE, biosignature, a blend of red and infrared lights reflected by plants. For example, a planet like Earth that is shrouded in a wilderness should have sections of strength for an easy-to-identify VRE signal. The JWST will quantify the VRE of distant Earth-like planets in the habitable zone around stars. They could be significant indications of something going on under the surface in the exoplanet environment. When sunlight crosses a planet star, the JWST might be ready to identify it as it enters its air. The light's missing frequencies would then be found via spectroscopy. Particles and atoms in the air absorb specific frequencies, making a characteristic fingerprint that the JWST can recognize. This method might be utilized to determine the creation of the atmosphere and whether life is conceivable. It is scientific that life could exist on Earth-sized planets with atmospheres like our own, with a predominance of oxygen, nitrogen, and carbon dioxide. By looking for elements that aren't generally present, one might have the option to distinguish mechanical life. Chlorofluorocarbons, CFCs, produced for use in refrigeration and cleaning products, would likely be recognizable to aliens checking Earth's atmosphere from a distance. If the JWST saw as CFCs in planetary climates, that sounds a really obvious sign of human advancement. As a matter of fact, life on exoplanets could not in any way, shape, or form look like life on Earth. Sometimes, even natural exact extremophile species can appear to be alien. This is a gathering of life forms, basically bacteria, that can get through conditions where other residing things would die. A few people can endure heat up to 250 degrees Fahrenheit. Some can endure colds as low as -4 degrees Fahrenheit. Some of them can get by in solid acids with pH levels under 3. While others can be seen as on Earth in where we wouldn't anticipate finding any life at all. But since planets like Earth are bound to help life than planets with severe temperatures or acidic circumstances, it very well may be a good thought to begin with those first. Prime candidates could have temperatures that permit liquid water to exist on their surfaces, as well as circle a stable star. The order for our Sun is a yellow G-type star. These stars are more rare and usually have shorter lives in our universe. The probability of considering planets circling around red small stars, which are more frequent and have lower glow and temperatures than the Sun, is higher. There is additional opportunity for the arrangement of life and evolution to produce complex life forms because these stars have considerably longer life expectancies. Around 40 light-years away from Earth, the TRAPPIST-1 planetary system will be the subject of JWST's first mission. It spins around a quiet red small star with 7 Earth-sized rocky planets. 3 of the rocky planets in the so-called habitable zone could have liquid water on their surfaces, despite having much smaller and colder mass than our Sun. The TRAPPIST-1 star emits light that is similar to that of Earth. The most obvious opportunity for people to see city lights outside the nearby planet group is Proxima Centauri, a red small star that is 4.25 light-years from the Sun and our nearest star. Proxima is around 600 times fainter than the Sun, so a planet should be multiple times closer to it than Earth is to the Sun for it to support life because of liquid water. In August 2016, space astronomers found a planet with 1.3 Earth masses in this habitable region in a Goldilocks-like habitable zone, where the light force is just right to melt water. Proxima B circles Proxima Centauri. It's possible that Proxima B is an airless, dormant planet given that it circles its red small star at a distance of just 4.6 million miles. The distance between the Sun and Earth is 93 million miles. The planet Proxima B is in a nearby circle that exposes it to strong solar winds that can completely destroy its atmosphere. It also provides enough sunlight for temperatures and liquid water that are similar to those on Earth. Because of its proximity to the star, Proxima B is thought to be tidally locked, continuously showing the same side to the star as the Moon does in reference to Earth. Proxima Centauri is around 1/8 the mass of the Sun and burns much less brightly than one would expect for a planet so close to its star. Only 5% of the world's Sun distance might be expected to be a scorching soot. Liquid water could easily exist on Proxima B as long as the planet has an atmosphere to hold heat in, since the total energy reaching it from the Sun is only 65% of what Earth gets. However, the planet isn't particularly friendly to life. It is indeed tidally locked, which means that it always faces the same direction toward the star and produces long-lasting, constantly agrees with significant temperature changes. The planet also gets 100-fold the amount high-energy radiation as Earth does because of its proximity to Proxima Centauri, including X-ray and ultraviolet light. Proxima B is also attacked with high-energy particles during star eruptions. Unless it has a preserving magnetic field like Earth's, however, there are certain favorable conditions that could make it a beautiful world. Unfortunately, models suggest that the atmosphere of tidally locked planets might be vulnerable to a rapid breakdown due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be refreshed by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we know nothing about Proxima B's volcanic activity or magnetic field strength, we couldn't figure out whether the planet has an air. But since an air surmises the presence of oceans, and the two taken together assume the presence of life, we are desperate to be aware in the event that Proxima B has a complex civilization. It could have sunlight-powered chargers covering the day side to produce power to light and warm the night side, which would somehow or another be excessively cold and dim for comfortable home. The discovery of Proxima B has set off a competition to determine if it crosses its star's face as seen from Earth. These travels would let scientists determine the planet's size and mass, which would then enable them to determine its density. Knowing that would approve the planet's rough makeup and give information on the materials used to make those stones. During a travel, starlight could reveal the nature of the planet by going through its environment, but the probability that the circle will be in the right arrangement so that scientists might see a travel is just 1 in 12%. The star's penchant to flare also confuses matters. Space astronomer David Kipping of Columbia College says the star is unstable as its intensity makes a rocky planet absorb daylight and transmit it as infrared light. However, rocky planets produce a particular type of infrared radiation from stars like Proxima Centauri. Moreover, the James Webb Space Telescope was made explicitly to concentrate on infrared light. Proxima B's infrared intensity mark is the way to recognizing the planet's air. Moreover, the infrared part of the range has a solid fondness for Hubble's replacement, potentially. Forever, researchers will actually want to measure how much water fume in the climate compels the overflow of various elements like carbon and oxygen and gauge the temperature of the air with profundity using the range that Webb is wanting to notice. They can utilize the information to draw conclusions about the planet's by and large piece, as well as how, when, and where it formed, the best fit model represented by the blue line on the diagram. The known qualities.